For as long as we have been human, we have been creatures of the question. We are born into a world of overwhelming mystery, and from the moment we can form a thought, we ask, why? We are pattern-seeking beings, storytelling animals. We look at the intricate, branching veins of a leaf and see the echo of a river delta seen from above. We gaze at the spiraling arms of a distant galaxy and see the familiar form of a seashell resting on the shore. And when we lift our eyes to the silent, humbling expanse of the night sky, we seek a narrative. We crave a story that places us within this vast cosmic drama. Where did all of this come from? How did it begin? For millennia, our answers were woven from the rich, vibrant tapestry of human imagination, faith, and philosophy. In the glow of ancient campfires, beneath the quiet gaze of the moon, our ancestors told stories that tried to make sense of it all. The Enuma Elish of ancient Babylon spoke of a universe born from the violent clash of the primordial gods Tiamat and Apsu, whose sundered bodies gave rise to the heavens and the earth. The Norse sagas told of a cosmos forged from fire and ice, a great void called Ginnungagap, from which the giant Ymir emerged, and from his body, the gods Odin and his brothers shaped the world. In the temples of ancient Egypt, they spoke of the watery chaos of Nun, from which the sun, god Ra, rose to bring light and order. The book of Genesis described a world spoken into existence from darkness by a single, all-powerful creator in a precise 6-day sequence. In the timeless verses of Hindu cosmology, the universe was not born once, but endlessly. An eternal rhythm of creation and destruction, the great cosmic breath of Brahma. Each cycle lasting more than 8 billion years. And in Islam, the story of creation is both majestic and profound. The Quran describes how Allah created the heavens and the earth in perfect harmony, not from chaos, but through divine command. Be, and it was. It tells us that the universe was once a joined entity, then separated, a description that echoes what modern science calls cosmic expansion. The message is clear. Creation itself is a sign, a reflection of divine power and wisdom. And as we explore these ancient stories, seeking meaning in the stars and in ourselves, take a moment to join this journey. If you're fascinated by the mysteries of the universe, by time, creation, and the questions that define our existence, make sure to like this video and subscribe to the channel. Your support helps us continue exploring the wonders that lie beyond the edge of the known cosmos. These were the original maps of reality. They were more than just early forms of science. They were profound attempts to find meaning, to offer not only an explanation for the world, but a sense of belonging within a cosmos that so often felt arbitrary, chaotic, and terrifying. They gave us a sense of home. Then, something changed. Slowly at first, then with gathering, world-altering force. A new way of knowing began to rise, a method not built on myth or metaphor, but on observation, measurement, and the courage to question. It was the birth of the scientific method. Alongside it came a new language to describe reality, one of breathtaking power and universality, the language of mathematics. Through this lens, humanity began to write a new creation story, not on stone tablets or sacred scrolls, but within the elegant equations woven into the very fabric of space and time itself. A story that came with a radical new promise. It could be tested, questioned, and, if the evidence demanded it, even overturned. For nearly a century, this scientific creation story has been the cornerstone of our understanding of the cosmos. It begins in a condition that defies all language, a state so extreme it shatters our most powerful ideas of space, time, and energy. It begins as a singularity, but that word, singularity, is not truly a description of a thing. It's the point at which our theories fail to describe what that thing could even be. A place of zero volume, infinite density, and unimaginable curvature, where the known laws of physics simply collapse. Within that infinitesimal point, all the energy, all the potential, and every future star, planet, and life form that would ever exist were contained, compressed into a condition of infinite temperature and infinite density. We gave it a name first spoken in mockery by the astronomer Fred Hoyle, who rejected the idea and favoured another, the steady state model. He called it dismissively this Big Bang idea. Yet the name endured, and it became the grand narrative of our universe. It's a story of explosive becoming, not an explosion in space, but an explosion of space itself. There was no outside for the universe to expand into, because the expansion created the very stage upon which everything would unfold. In that first, unimaginably brief instant, from 10 to the minus 36 seconds to 10 to the minus 32 seconds, the universe experienced a phase of violent hyperacceleration known as cosmic inflation. Driven by the energy of a mysterious quantum field, the universe expanded by a factor of at least 10 to the 26, growing from far smaller than a proton to larger than a galaxy, in less time than it takes light to cross an atomic nucleus. This astonishing burst smoothed away any wrinkles or curves in spacetime, explaining why today the universe appears so remarkably flat on cosmic scales. It also stretched the tiny quantum fluctuations of the early vacuum to astronomical sizes, seeding the structure of everything that would follow, from galaxies to stars to worlds like our own. As inflation ended, the energy of that field transformed into a storm of fundamental particles, heating the newborn cosmos to a searing 10 to the 27 degrees. The universe became a glowing ocean of quarks, gluons, electrons, and photons, a quark-gluon plasma, dense and chaotic beyond imagination. For the first microsecond, quarks could not yet bond together. But as expansion continued and the cosmos began to cool, the first protons and neutrons emerged, the earliest building blocks of everything that would ever be. The story of modern cosmology, of how we came to understand the universe, is written in equations, starlight, and the persistence of human curiosity. It's the story of the Lambda cold dark matter model, the framework that underpins everything we know about the cosmos. But it is also a story of disagreement, revolution, and the courage to challenge even the grandest ideas. It began, in a sense, with a man who bridged two worlds, Georges Lemaitre. He was both a Belgian priest and a brilliant theoretical physicist, a man who showed that science and faith were not enemies, but partners in the search for truth. In the 1920s, Lemaitre worked through the intricate equations of Einstein's newly minted theory of general relativity. What he found was astonishing. The equations didn't allow for a static, unchanging universe. The cosmos, according to Einstein's own math, must be either expanding or contracting. Lemaitre took that idea further. If the universe is expanding today, he reasoned, then it must have been smaller, denser, and hotter in the past, perhaps once condensed into a single, fantastically dense point, which he called the primeval atom, or the cosmic egg. When Lemaitre shared this idea with Einstein in 1927, the great physicist dismissed it outright. Einstein had introduced a term, the cosmological constant, into his equations specifically to keep the universe static. He famously told Lemaitre, "Your calculations are correct, but your physics are abominable." But 2 years later, the universe itself would prove Lemaitre right. In 1929, at the Mount Wilson Observatory in California, an American astronomer named Edwin Hubble used the world's most powerful telescope, the 100-inch Hooker, to study distant spiral nebulae. By identifying a special kind of pulsating star called a Cepheid variable in the Andromeda Nebula, Hubble was able to calculate its distance with precision. The result stunned the scientific world. Andromeda was nearly 1 million light-years away, far beyond the boundaries of the Milky Way. The spiral nebulae weren't clouds within our galaxy. They were galaxies themselves, vast island universes drifting in the cosmic sea. Hubble went further. By measuring the spectral lines of these galaxies, he discovered that almost all of them were redshifted. Their light stretched toward the red end of the spectrum, meaning they were moving away from us. And the farther away they were, the faster they receded. The universe was expanding. Einstein, confronted with the evidence, visited Hubble at Mount Wilson. He admitted that his insistence on a static cosmos had been, as he put it, the greatest blunder of his career. But as we looked deeper into this expanding universe, new mysteries began to surface. Mysteries that would redefine everything we thought we knew. In 1933, the brilliant and notoriously irritable Swiss-American astronomer Fritz Zwicky was studying the Coma Cluster, a vast congregation of over 1,000 galaxies. He measured their velocities and found that they were moving so fast that, by all accounts, the cluster should have been flying apart. The visible matter, the stars, the glowing gas, simply wasn't enough to account for the gravitational pull holding it all together. There had to be something else, something unseen. Zwicky proposed a daring idea, that the universe was filled with an invisible form of matter, providing the hidden gravity that bound galaxies and clusters together. He called it Dunkel Materie, dark matter. His idea was so radical, so ahead of its time, that it was largely ignored for the next 40 years. But the universe has a way of bringing the truth back into focus. In the 1970s, the idea of dark matter was resurrected by the meticulous and groundbreaking work of American astronomer Vera Rubin. She studied how individual galaxies rotated, the way stars orbit around their centers. According to Newton's laws, the stars at a galaxy's edge should move more slowly than those near its core, just as the outer planets in our solar system move more slowly than the inner ones. But Rubin, working with her colleague Kent Ford and using highly sensitive spectrographs, discovered something astonishing. The stars on the outskirts were moving just as fast as those near the center. The rotation curves were flat. The only explanation was that each galaxy was enveloped in a vast invisible halo of unseen matter, an immense sphere of dark material that extended far beyond the visible light. Rubin's careful and repeated measurements made the conclusion undeniable. dark matter was no longer just a theory. It had become a cornerstone of modern cosmology. Today, the evidence for dark matter is overwhelming, but perhaps the most powerful and visually stunning clue comes from what astronomers call the Bullet Cluster, a haunting cosmic photograph showing two massive galaxy clusters that have recently collided and passed through each other. When we look at this celestial crash in different wavelengths of light, a hidden truth begins to reveal itself. In visible light, we see the brilliant glow of billions of stars spread across both clusters. In X-rays, we see something even more telling: the enormous clouds of superheated gas, the main form of visible matter in the universe. These clouds have slammed into each other, slowing down and piling up in the middle, forming a glowing scar of shock waves millions of light years across. But then comes the twist, the key to the invisible. Using gravitational lensing, the bending of light from even more distant galaxies behind this scene, scientists can map where the true mass of the system lies. And what they found was astonishing. The majority of the mass wasn't with the glowing gas in the center at all. Instead, it existed in two ghostly bullet-shaped regions on either side, regions that had passed straight through the collision unaffected. This was the smoking gun. Dark matter is real. It interacts through gravity, but not through any of the familiar forces that affect ordinary matter. It moves like a swarm of invisible phantoms, silent, collisionless ghosts haunting the cosmic stage. But the story doesn't end there. The strangest twist of all came in 1998, a year that forever changed our understanding of the universe. Two teams of astronomers, working half a world apart, were hunting for clues about how fast the universe was expanding. One team was led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees. Their method was ingenious. They studied distant Type 1A supernovae, the thermonuclear explosions of dying white dwarf stars. These explosions always shine with nearly the same intrinsic brightness, which means that by measuring how faint they appear, you can calculate exactly how far away they are. The scientists expected to find that the universe's expansion was slowing down over time, pulled back by gravity. But the data told a completely different story. The distant supernovae were dimmer than expected. They were farther away than they should have been. And there was only one explanation. The expansion of the universe wasn't slowing down. It was speeding up. Some mysterious force was pushing the cosmos apart with ever-increasing speed. They had stumbled upon one of the greatest discoveries in the history of science, the existence of dark energy, a strange, repulsive pressure embedded deep within the very fabric of space-time itself. And suddenly, Einstein's so-called biggest blunder, his idea of a cosmological constant that he once rejected, came roaring back as our best description of this cosmic acceleration. The name of our grand model became the Lambda Cold Dark Matter Model, a universe made of only 5% normal matter, 27% ghostly dark matter, and a staggering 68% mysterious dark energy. This became the foundation of modern cosmology, a model so powerful that it could explain nearly everything we see in the sky, from the abundance of hydrogen and helium forged in the first few minutes after the birth of the cosmos, to the vast web of galaxies stretching across billions of light years. It was one of humanity's greatest triumphs, proof that through persistence, imagination, and the power of reason, we could begin to read the mind of the universe itself. But even before the James Webb Space Telescope opened its golden eye to the cosmos, the triumphant model of our universe was beginning to show signs of strain. A hairline fracture had appeared in its magnificent facade, a problem that started as a small curiosity and grew into a full-blown cosmic crisis. Astronomers call it the Hubble tension. The Hubble constant, often called H0, is one of the most important numbers in all of cosmology. It tells us how fast the universe is expanding right now. And for the past decade, the two best and most precise ways we have to measure it have been giving us two different answers. This isn't a small disagreement. It's what scientists call a 5 sigma result, meaning there's less than a 1 in a million chance that it's a random mistake. The first way to measure it comes from what we call the early universe. It uses the oldest light in existence, the faint afterglow of creation itself, the cosmic microwave background. Satellites like Planck have mapped this ancient light in astonishing detail. It shows us the universe as it was just 380,000 years after the beginning. A cosmic baby photo. Tiny ripples in temperature across that image are the quantum fingerprints of everything that would later become galaxies, stars, and planets. By studying the size and pattern of those ripples, cosmologists can do something remarkable. They take the lambda cold dark matter model, feed in those early conditions, and run the cosmic clock forward for 13.8 billion years. The model predicts exactly how fast the universe should be expanding today. It's like finding the fossil of a dinosaur embryo and using biology to predict precisely how tall the adult would have been. This early universe method gives a Hubble constant of about 67 kilometers per second per megaparsec, meaning that for every 3.26 million light-years of distance, a galaxy moves away from us 67 kilometers per second. The second way to measure it is completely different. It doesn't rely on theoretical models at all. It measures the expansion rate directly in what astronomers poetically call the cosmic distance ladder, a careful, step-by-step chain of measurements that stretches from nearby stars all the way to the edge of the visible universe. The first step is parallax. By observing a nearby star from two opposite points in Earth's orbit, we see a tiny shift in its position against the background stars. The same trick your eyes use to sense depth. That gives us a precise distance. The second step uses Cepheid variable stars. These are stars that pulse in brightness with a rhythm tied to their true luminosity. By measuring that rhythm and comparing how bright or faint they appear, astronomers can measure how far away they are, even in distant galaxies. The third step is the Type 1, a supernova. These are cataclysmic explosions of white dwarf stars that shine with nearly identical brightness every time. For a short while, they can outshine their entire galaxy. A few galaxies contain both Cepheid stars and one of these supernovae, allowing astronomers to calibrate them perfectly, turning them into cosmic lighthouses visible across billions of light years. By comparing the distance of these far-off supernovae with their redshift, how much their light has been stretched by the expansion of space, scientists can measure the expansion rate directly right now in the modern universe. This late universe method gives a Hubble constant of about 73 kilometers per second per megaparsec. And there it is, the crisis. 67 versus 73. The prediction from the early universe doesn't match the measurement from the late universe. It's as if our biological model predicted that an adult dinosaur would be 67 feet tall, but when we find the fossil, it stands 73 feet tall. Something doesn't add up. Either the measurements are flawed in some hidden, systematic way that no one has yet uncovered, or the great cosmic rulebook we've been using, the Lambda cold dark matter model, is wrong, or at least incomplete. And this was the cosmic mystery waiting in the darkness when the James Webb Space Telescope took flight. The grand edifice of modern cosmology was already showing a deep and growing crack. And then, Webb turned its gaze toward the foundation itself. The James Webb Space Telescope is not just a successor to Hubble. It is something far more ambitious, a fundamentally different kind of instrument, built to ask deeper, more profound questions. Its story is a human epic, a tale of perseverance, ingenuity, and the relentless desire to see the unseen. Conceived in the late 1980s, even before Hubble had launched, it was first called the Next Generation Space Telescope. Astronomers knew that to glimpse the very first stars and galaxies, they would need a telescope unlike any before it, one that was enormous to collect the faint ancient light of the cosmic dawn, and one that was unimaginably cold. Because it would be searching for the faint heat signatures of the early universe. Any warmth from the telescope itself would blind it. That meant it couldn't orbit Earth like Hubble. It had to go much farther, nearly 1 million miles away, to a special point in space known as the second Lagrange point, or simply L2. This is a gravitational sweet spot where the combined pull of the Sun and the Earth allows a spacecraft to remain in a stable orbit, trailing the Earth as it moves around the Sun. From this vantage point, the Earth, Moon, and Sun always lie in the same direction, letting the telescope hide behind a massive sunshield and stay forever in darkness. The engineering challenges were staggering. The primary mirror needed to be 6.5 meters across, more than 21 feet, to gather enough light, but no rocket could possibly fit a mirror that large. The solution was ingenious: a segmented mirror made of 18 hexagonal pieces that would fold up like origami for launch, and then unfold once in space. Each segment was crafted from beryllium, a metal both incredibly strong and light, and coated with a thin layer of pure gold, chosen because gold reflects infrared light better than any other material known. And then there was the sunshield, a technological marvel in its own right. To keep the telescope cold enough to detect the faint heat from the first galaxies, it needed protection from the scorching light of the Sun, Earth, and Moon. Engineers designed a 5-layer parasol the size of a tennis court. Each layer, made of an advanced material called Kapton, is thinner than a human hair and coated with aluminum and silicon. Together, these layers act like a cosmic thermos. The outer side bakes at about 85 degrees Celsius, while the inner side, where the telescope sits, chills at a mind-numbing minus 233 degrees Celsius. Building it took more than 25 years. Costs rose from an expected $1 billion to an almost unbelievable $10 billion. It endured delay after delay and came within a single congressional vote of being cancelled altogether. But the passion of the scientific community kept it alive. Entire careers were spent creating the technologies needed to make it possible. 10 of them invented entirely from scratch. Then came the moment of truth. Launch day, Christmas morning, 2021. What followed was a 30-day, million-mile journey of almost unbearable tension. The telescope had to unfold in space through a series of 344 separate mechanisms, each one a single point of failure. If even one jammed or misfired, the telescope would be lost forever. The world watched as the sun shield unfolded, its layers stretched and locked into place, and the golden mirrors blossomed open one by one. Against all odds, every mechanism worked flawlessly. The most complex deployment in the history of space exploration had succeeded. When it finally opened its golden eye to the universe, humanity had built a true time machine, capable of looking back more than 13 billion years to witness the birth of the first stars and galaxies. But when it began to see, what it saw was something no one had expected. In the summer of 2022, when the first scientific data began streaming down from the telescope's 4 state-of-the-art instruments, the astronomical community was electrified. Teams working on deep field programs like the Cosmic Evolution, Early Release Science Project, and the Advanced Deep Extragalactic Survey pointed the telescope toward regions of sky that once appeared completely empty, letting ancient light collect for hours upon hours. At first, the reaction was pure joy. The images were deeper, sharper, and more breathtaking than anyone had imagined. But as the data poured in and researchers began analyzing the faint reddish smudges, those fragile signatures of the earliest galaxies, a strange feeling began to spread. Excitement slowly turned into confusion, and then into something almost like fear, because the galaxies were all wrong. This was the problem astronomers soon called too much, too soon. It was a triple mystery, each piece more unsettling than the last, and together they struck at the very heart of modern cosmology. The first problem was mass, the discovery of what scientists began calling the impossibly early galaxies. Our understanding of the universe has always been a story of slow construction, a bottom-up model. Small things form first. Tiny stars merge into clusters, clusters into small galaxies, and over billions of years, those small galaxies grow into vast spirals and ellipticals. It's like building a castle out of Lego bricks. You start with a few pieces, make small walls, and only after a long time do you end up with something magnificent. But the telescope found something that shattered that logic. Galaxies that seemed to contain 10 billion suns, or even more, appearing just 400 to 500 million years after the Big Bang. That's far too early. By all accounts, they shouldn't exist. It's like finding a modern skyscraper standing tall in a painting of ancient New York from the 1700s. Not just unexpected, impossible. The universe, as we understand it, operates on a cosmic matter budget. There's only so much ordinary matter, baryonic matter, available to build stars and galaxies. And even in the best conditions, star formation is incredibly inefficient. A bright young galaxy might convert just 10% of its gas into stars before radiation and supernova explosions blow the rest away. But when University of Texas astronomer Mike Boylan Colchin ran the numbers, what he found was astonishing. These early galaxies would have had to convert nearly 100% of all the available gas and dark matter into stars. something nature simply doesn't allow. It's like being handed a single tree and somehow constructing an entire mansion out of it. It violates the most basic law of conservation of matter. And that's why these galaxies are called the impossible early galaxies. Because if they truly exist, they don't just challenge our equations, they challenge our entire understanding of how the universe was built. The second problem is metallicity, and it cuts even deeper. In astronomy, the periodic table is simple. There's hydrogen and helium, created in the Big Bang, and then there's everything else. Astronomers call all of it, quite conveniently, metals. These metals, elements like carbon, oxygen, nitrogen, and iron, are forged inside stars. When those stars die, they scatter their ashes across the universe, enriching the next generations of stars and planets. So, a high metallicity tells a story of age, of countless births and deaths of stars. It's a signature of cosmic maturity. The very first stars, what scientists call population 3, should have been made of nothing but hydrogen and helium, pure and untouched. The second generation, population 2, would have just a trace of metals. Our own sun belongs to population 1, with about 2% metals, meaning it's been recycled through many generations of star birth and death. The telescope spectrographs were designed to analyze the light from the oldest galaxies, breaking it apart to reveal their composition. Everyone expected to see the pure, metal-free fingerprints of the early universe. But what they found was shocking. Galaxies already rich in metals. Clear chemical traces of oxygen, nitrogen, and carbon appeared where there should have been only pristine hydrogen and helium. It was like finding a brand new car that already had rust, a history that shouldn't exist yet. Even more surprising, the telescope found something else. Dust. Not the kind of dust that gathers under your bed, but cosmic dust. Microscopic grains of silicate and carbon, born in the cool, outer layers of dying stars and in the explosive chaos of supernova. Dust takes time to make, lots of it. Yet, here it was, only a few 100 million years after the Big Bang. As astronomer Emma Chapman put it, it's like discovering a Roman coin sealed inside an ancient Egyptian tomb. The coin belongs to a later era, and its presence rewrites the timeline. These galaxies seem to have lived fast and died young, forming stars, producing metals, and filling space with dust at a pace that defies the limits of physics as we know them. And then came the third problem: structure. The early universe should have been a violent, chaotic place. Tiny proto-galaxies colliding, merging, tearing each other apart in a cosmic demolition. Derby. It was supposed to be messy. That chaos was how galaxies grew. And it would take billions of years for the wreckage to settle into something smooth, something ordered, like a spiral galaxy. A large, well-organized disk, like the Milky Way or Andromeda, is a symbol of peace after cosmic war. It takes time for gravity to pull stars into stable orbits, for the chaos to calm into beauty. The dark matter halo acts as the invisible skeleton, guiding this transformation, but slowly, gently, over eons. So scientists expected to see galactic wrecks, and the telescope did find them. Irregular, clumpy, turbulent systems. But it also found something no one anticipated. Beautiful, perfectly formed disks. Galaxies that looked normal, peaceful, structured, existing less than 1 billion years after the Big Bang. They were smaller than galaxies like ours, but astonishingly organized, far too organized for their age. It was like looking at a kindergarten photo and seeing several of the children holding PhD diplomas in astrophysics. These galaxies weren't supposed to exist, not yet. And their quiet, ordered beauty has left cosmologists scrambling for answers, wondering how the universe could grow up so quickly, so impossibly early in its history. When a beautiful, elegant, and long-cherished theory collides with a fleet of ugly, undeniable facts, the very soul of science is laid bare. At first, there's denial, a desperate hope that the data is wrong. Then comes the checking, the rechecking, the endless recalibrations. But when the facts refuse to bend, when independent teams using different methods arrive at the same impossible conclusion, a reckoning begins. We are now living in that moment. It is a time of thrilling intellectual combat, of sleepless creativity and bold ideas. The halls of astronomy echo with the energy of discovery not seen in decades. The mysterious galaxies revealed by the Space Telescope have ignited a scientific firestorm, dividing the field into two great camps, the reformers and the revolutionaries. The reformers are not ready to burn down the magnificent house of modern cosmology. They argue that a theory capable of explaining the cosmic microwave background, the light elements of the Big Bang, and the grand web of galaxies across the universe cannot be entirely wrong. The foundations, they say, are solid. The problem must lie in the details, in the messy, uncertain physics of galaxy formation. Their mission is not to destroy, but to rebuild. To them, the universe clearly has a mechanism, a kind of cosmic cheat code, that allows galaxies to grow far faster than we imagined. The quest is to find that code. One of the most compelling possibilities comes from a ghost of the universe's first moments, primordial black holes. This is not a new or desperate idea. It was first proposed in the 1960s by Soviet physicists Yakov Zeldovich and Igor Novikov, and later developed by a young Stephen Hawking in 1971. Their reasoning came directly from the physics of inflation. The idea that, in the first instant after the Big Bang, the universe expanded faster than the speed of light, stretching tiny quantum fluctuations into the seeds of galaxies. But what if some of those fluctuations were not so gentle? Imagine the early universe as a vast landscape of hills and valleys, and the energy of creation as a ball rolling across it. In most places, the slope was smooth and steady, but in some rare patches, the landscape may have had deep dips, moments when the ball slowed down just long enough for quantum ripples to grow dense and powerful. When inflation ended, those tiny, overdense regions could have collapsed under their own gravity, forming black holes directly from energy itself, no stars required. These were not the familiar black holes born from dying stars. These were true relics of the beginning, black holes from the first second of time. Their masses could vary wildly, depending on when they formed. Some might weigh as little as an asteroid. Others could be as massive as the moon, a planet, or even 1,000 suns. Scattered through the fog of the early universe, they would have acted as gravitational superpowers. In the standard picture, galaxy formation is slow and patient, a bottom-up process. Tiny fluctuations in density gradually pull in matter over hundreds of millions of years. But primordial black holes change that story entirely. A single one could act as an anchor, a gravitational magnet, pulling in gas, dark matter, and radiation from all directions. In regions lucky enough to contain clusters of these invisible giants, galaxies could form in a cosmic heartbeat. This could explain the too massive, too soon problem. Those impossibly large galaxies seen in the early universe. It gives them a natural head start, a way to gather 1 trillion suns worth of material long before physics says they should have existed. And the idea is even more tempting because it offers bonus answers to other cosmic mysteries. For one, it could explain the supermassive black holes powering the first quasars, objects that shine with the brightness of entire galaxies, yet existed when the universe was still in its infancy. Growing a 1 billion solar mass black hole from a dead star in only a few 100 million years seems impossible. But if a massive primordial black hole was already there from the start, the puzzle suddenly fits. Even more enticing if enough of these primordial black holes exist, particularly those in the asteroid to moon mass range. They could be the very thing we call dark matter. The invisible web binding the cosmos together wouldn't require any exotic new particles at all. It would simply be made of ancient black holes, silent, invisible remnants of the Big Bang itself. One elegant idea, solving 2 of cosmology's greatest mysteries in a single stroke. However, if primordial black holes are truly the answer, we are faced with a pressing question. Where are they? The primordial black hole model is not a free-for-all. It is one of the most heavily constrained ideas in cosmology. For 50 years, astronomers have been hunting for them, and their failure to find them has ruled out many possibilities. First, evaporation. Stephen Hawking's most famous discovery was that black holes are not truly black. They evaporate over time by emitting what's known as Hawking radiation. The smaller the black hole, the faster it evaporates. Any primordial black holes with a mass less than about 1 billion tons, roughly the mass of a large mountain, would have evaporated by now, releasing their energy in a final flash of gamma rays. Our measurements of the cosmic gamma ray background form a firm wall of evidence. They tell us that no significant population of these low-mass primordial black holes can exist. Next, gravitational lensing. For larger primordial black holes, from the mass of the Moon up to 1,000 times the mass of our Sun, the primary search method is gravitational microlensing. Einstein's theory of general relativity tells us that mass bends space-time. If a primordial black hole passes between us and a distant star, its gravity acts like a lens, briefly and characteristically brightening that star's light. Large-scale surveys like Macho, Eros, and Ogle have watched millions of stars in our galaxy for decades, searching for these telltale flickers. They have found some, but not nearly enough to account for all the dark matter. These observations have placed severe limits, suggesting that primordial black holes in this mass range can make up only a tiny fraction of the dark matter halo. Then there's accretion. If primordial black holes are floating around, they should be feeding. As gas falls onto them, it heats up and emits radiation. If they make up the dark matter, this accretion process in the early universe would have injected huge amounts of energy into the primordial plasma, distorting the perfect blackbody spectrum of the cosmic microwave background. In the 1990s, the COBE-FIRIS instrument measured this spectrum with incredible precision and found it to be one of the most perfect blackbodies ever observed in nature. That result placed extremely tight limits on how many primordial black holes could have been accreting in the early universe. Finally, dynamical effects. A universe filled with dense, massive objects would be a chaotic place. The gravitational pull of primordial black holes would disrupt the orbits of wide binary stars, puff up the centers of faint dwarf galaxies, and alter the overall structure of the cosmos. Each of these clues adds another layer of constraint. When we put all of these limits together, it seems like the primordial black hole model is in serious trouble. There are only a few narrow, unexplored windows of opportunity left. The most prominent is what scientists call the asteroid mass window, for primordial black holes between the mass of a small asteroid and the mass of the Moon. They are too big to have evaporated, yet too small to have been effectively detected by microlensing. Could these be the dark matter? Could clusters of them have served as the first seeds of galaxies? It's possible. The discoveries made by the James Webb Space Telescope, while not direct evidence for primordial black holes, have provided powerful motivation for the scientific community to re-examine these constraints and find new, ingenious ways to search for these ancient ghosts of the Big Bang. A second avenue of reform focuses not on exotic gravity, but on exotic stars. Maybe our understanding of the first stars, the mysterious population 3 stars, is far too conservative. For years, computer simulations have portrayed them as being extremely massive, perhaps a few hundred times the mass of the Sun. The logic seems sound. The primordial gas from which they formed was made of only hydrogen and helium, the simplest elements. These elements are very inefficient at cooling. In modern star-forming clouds, heavier elements like carbon and oxygen act like thermostats, radiating away heat and allowing the cloud to fragment into many small, dense cores that form stars like our Sun. Without these cooling agents, the primordial clouds stayed hot. They could only collapse when they became incredibly massive, leading to the birth of enormous, isolated stars. But what if enormous is an understatement? Some new models, championed by astronomers such as Volker Braun at the University of Texas, propose that under certain rare but crucial conditions, the first stellar objects could have been true supermassive stars, reaching up to 100,000 times the mass of our Sun. These are not really stars in the traditional sense. They are more like temporary, bloated, hyperluminous gas clouds. They form in regions where the inflow of primordial gas is so immense and so rapid, 1,000 times more intense than in a normal star-forming region, that it triggers a runaway collapse. In this scenario, a central seed black hole forms, perhaps from a normal population 3 star. But the rain of gas is so relentless that it overwhelms the star. A vast, bloated envelope of gas, hundreds of times the size of our solar system, forms around the growing black hole. The object becomes what astronomers call a quasi-star. Its immense luminosity comes not from nuclear fusion in its core, but from the heat generated by the gas crashing into the central black hole. It is a star powered not by fusion, but by accretion. Such a giant would be wildly unstable, shining with the brilliance of 1,000,000 suns for perhaps 1,000,000 years, before the central black hole becomes massive enough to devour its entire gaseous shell and collapse. This provides a natural and elegant way to create the heavy seeds for the supermassive black holes we observe in the earliest quasars. A quasi-star collapsing when the universe is only about 150 million years old could leave behind a black hole with 10,000 times the mass of the Sun, giving it an enormous head start. This neatly solves one of cosmology's most persistent mysteries. Furthermore, the death of these first-generation stars, whether normal population 3 giants or supermassive quasi-stars, would have been the engine of early chemical enrichment. A 200 solar mass star, for example, would not die in a normal supernova. It would become so hot in its core that it begins to produce vast numbers of electron-positron pairs, which reduces the internal pressure and triggers a runaway thermonuclear explosion known as a pair instability supernova. Unlike a typical supernova that leaves behind a black hole, this type of explosion tears the entire star apart, scattering all of its heavy elements, including enormous amounts of carbon, oxygen, and silicon, into the surrounding space. One such explosion could enrich an entire region of the early cosmos to a metallicity level comparable to what the James Webb Telescope is now observing. These ancient explosions would also have been powerful factories of cosmic dust, which helps explain the surprisingly dusty nature of the first galaxies. The final reformist proposal is less about creating new objects and more about feeding them faster. What if the process of star and galaxy growth itself was hyper-efficient in the early universe? The rate at which a star or black hole can grow is thought to be limited by a fundamental principle of physics called the Eddington limit. It's a beautifully simple balance. Gravity pulls gas inward, while the radiation produced by that falling gas pushes outward. The Eddington limit marks the point where these two forces perfectly cancel. Try to feed the object any faster, and the light pressure acts like a cosmic hurricane, blowing the incoming material away. For decades, scientists treated the Eddington limit as an unbreakable speed limit. But what if, in the chaotic and extreme environment of the early universe, this limit could be temporarily broken? This process, known as super-Eddington accretion, could allow black hole seeds or dense star clusters to grow exponentially faster than previously thought. How could this happen? One possibility is clumpy accretion. The Eddington limit assumes that the infalling gas is smooth and uniform. But what if it isn't? If the gas is clumpy and porous, radiation can escape through the low-density gaps, while the denser clumps of gas push their way inward. It's like the difference between trying to pour water onto a powerful fan versus throwing small stones at it. The water gets blown back, but the stones punch right through. Another mechanism is photon trapping. In extremely dense accretion flows, the photons produced near the black hole can become trapped by the infalling gas and dragged inward before they ever escape. This effectively removes the outward pressure that would normally halt the infall, allowing matter to stream inward far more rapidly. Alongside these exotic feeding mechanisms comes the idea of exotic delivery. Our standard models often assume that gas falls onto a young galaxy from all directions, forming a large, hot, turbulent halo. This is called hot mode accretion. The gas in this state must cool over millions of years before it can form stars, a major bottleneck in galaxy growth. But large-scale computer simulations of the cosmic web have revealed a different, far more efficient mechanism: cold stream accretion. In this model, the universe is a vast web of structure, huge empty voids connected by long, dense filaments. galaxies form where these filaments intersect at the nodes of this cosmic network. Simulations show that much of the primordial gas never gets shock heated in a halo. Instead, it flows along these narrow, dense, cold filaments directly into the centers of young galaxies. These streams act like cosmic highways, delivering a constant supply of cold, ready-to-use fuel for star formation, bypassing the slow cooling stage entirely. These are the main tools in the Reformer's arsenal: primordial black hole seeds, supermassive first stars, and hyper-efficient accretion flows. Each offers a physically plausible, though not yet proven, way to accelerate the cosmic timeline. They are attempts to turn up the dial on the universe's stellar engine, to see if it could run faster and hotter than anyone ever imagined. They push the boundaries of astrophysics to their very limits, yet they do so while keeping the fundamental framework of the Big Bang intact. Then there is the second camp, the revolutionaries. They look at the JWST data and see something far more profound than a puzzle. They see a contradiction, a falsification. To them, this isn't a crack in the plaster that can be repaired. It's a sign that the very foundations are unstable, that the framework itself, the assumption of a 13.8 billion-year-old universe born from the Lambda CDM Big Bang, may be broken. For the revolutionaries, it's not time for renovation, it's time for a revolution. One of the most mind-bending, yet strangely elegant of these revolutionary ideas is the concept of a cyclical universe. What if the Big Bang wasn't the beginning, but merely the latest bang in an endless rhythm of cosmic expansion and contraction? The idea of a repeating universe is ancient, woven into the philosophies of many early civilizations. But in modern physics, it takes on mathematical precision. One of the most developed versions of this idea is the Big Bounce, which emerges from a theory of quantum gravity known as loop quantum gravity, or LQG. LQG, a rival to string theory, attempts to quantize spacetime itself. In this picture, space and time are not smooth and continuous. At the tiniest Planck scale, they are built from discrete, indivisible loops, atoms of space-time. This changes everything. In Einstein's general relativity, the Big Bang is a singularity, a point of infinite density where space-time itself ceases to exist. But in LQG, infinite density is impossible. You cannot compress matter into a volume smaller than one of these quantum atoms of space. So, as the universe contracts and density climbs toward the Planck scale, gravity doesn't become infinite, it flips. A new, powerful repulsive force emerges from the quantum geometry of space-time itself. Gravity, at the ultimate scale, turns outward. The collapse halts, the universe rebounds, a bounce, expanding again into a new cosmic epoch. The singularity is erased, replaced by a quantum bridge to a previous universe. Another flavor of this cyclical idea comes from string theory, specifically M-theory, known as the ekpyrotic universe, from the ancient Stoic term for a cosmic fire. This model, developed by Paul Steinhardt and Neil Turok, envisions our universe as a three-dimensional brain floating in a higher dimensional space. Another brain exists parallel to ours. In this model, the Big Bang was not a birth, but a collision. Two brains slamming together, converting their enormous kinetic energy into the heat and matter of a new expanding universe. The cosmos then expands, cools, and grows empty due to dark energy. After trillions of years, the brains are drawn together again. They collide, and the cycle repeats forever. a cyclical universe would beautifully resolve the JWST's timeline crisis. The galaxies we see didn't need to form in just a few 100 million years. They could be ancient survivors, relics from a previous cosmic era, carrying their mass, metals, and black holes through the bounce into our current epoch. The Big Bounce or brain collision would not be a total reset. It would be more like a cosmic purification, shedding the diffuse outskirts of galaxies while preserving their dense cores. These recycled galaxies would emerge already mature, already structured. It's a vision as philosophically profound as it is scientifically daring. An eternal cosmos, inhaling and exhaling through infinite cycles. A cosmic breath without beginning or end. But this idea faces immense physical challenges. The first is the entropy problem. The second law of thermodynamics dictates that entropy, or disorder, always increases. In a cyclic universe, each bounce should therefore be larger and longer than the last. Run this process backward, and you still approach a beginning, a first cycle. Some theorists propose mechanisms to reset cosmic entropy between bounces, but these remain speculative. Next comes the homogeneity and flatness problem. Our universe is astonishingly smooth and geometrically flat. The standard Big Bang model explains this with cosmic inflation, a brief moment of exponential expansion. A cyclic model must find its own explanation for this smoothness, either incorporating inflation in every cycle or developing an entirely new mechanism that can iron out the wrinkles of space-time before each bounce. And finally, perhaps the greatest question of all: how could delicate galactic structures survive such an apocalyptic event? Could black holes, stars, and clusters truly endure a bounce or a brain collision intact? These questions live today not in observatories, but on the chalkboards and supercomputers of theoretical physicists, still far from experimental reach. This crisis has even led a small but vocal group of scientists to reopen the oldest debates in cosmology, arguing that perhaps the field took a wrong turn nearly a century ago. Among these revived ideas is the tired light hypothesis, first proposed in 1929 by Fritz Zwicky, the same scientist who discovered dark matter. It suggests that the cosmological redshift is not caused by the expansion of space at all. Instead, photons lose energy gradually as they travel across vast cosmic distances, perhaps through interactions with some unknown particle or plasma. This slow energy loss would make the light appear redder, mimicking the Doppler effect of an expanding universe. In this view, the universe is not expanding. It is static, infinite, and ageless. This idea was eventually dismissed by most of the astronomical community because it failed to explain several critical observations that the Big Bang model had already predicted with remarkable accuracy. For example, there is the faint, uniform, 2.7 Kelvin thermal glow coming from every direction in the sky, known as the cosmic microwave background. A static, eternal universe offers no natural reason for its existence, while the Big Bang model predicted it perfectly as the leftover heat from an early, hot, and dense universe. Not only does this background exist, but it also carries an almost perfect blackbody spectrum, a thermal fingerprint that could only have formed in a universe that was once in equilibrium. Then there is the strange phenomenon of time dilation in supernova. In an expanding universe, distant cosmic events don't just look redder, they appear to unfold in slow motion, stretched by the expansion of space itself. When astronomers observe faraway supernovae, they see exactly this effect. Their light curves, the way their brightness rises and falls, are stretched by precisely the amount predicted by their redshift. A static, tired light universe where photons simply lose energy can't explain this slow-motion behavior. Finally, there is the surface brightness test. In an expanding universe, as light from a distant galaxy travels toward us, it spreads out over a larger apparent area, making the galaxy appear dimmer in a very specific way. Observations match this prediction perfectly, while a static model fails to reproduce it. Despite these major shortcomings, a small group of researchers kept the idea alive. Among them is physicist Eric Lerner, who reimagined it through the lens of what's called plasma cosmology. Lerner argues that the universe is not ruled solely by gravity, but by powerful electromagnetic forces acting through vast cosmic plasmas. In this vision, galaxies, clusters, and even large-scale cosmic filaments are shaped by the behavior of charged particles and magnetic fields. From this perspective, the recent observations aren't anomalies at all. They're confirmations. If the universe is infinitely old, there has been more than enough time for massive, mature galaxies to form everywhere. Lerner and other plasma cosmologists reinterpret the cosmic microwave background not as ancient radiation from a hot beginning, but as the collective radio glow of countless distant galaxies, thermalized by webs of plasma that fill intergalactic space. They also suggest that the observed abundance of helium and other light elements could have formed through the nuclear processes of early generations of massive stars, rather than in a primordial explosion. Although these ideas are held by only a small minority of scientists and are widely rejected due to the overwhelming success of the standard cosmological model, the new findings have given them a momentary spotlight, an opportunity to challenge what has long been accepted as unshakable truth. Amid these debates stands one of the most fascinating and scientifically respected alternative ideas: modified Newtonian dynamics, or EMOND. In the early 1980s, Israeli physicist Mordechai Milgram asked a question so bold that it still echoes through cosmology today. What if dark matter doesn't exist at all? What if the problem isn't missing mass, but our understanding of gravity itself? Milgram proposed that Newton's famous law of gravity, which states that the force of attraction weakens with the square of the distance, might not hold in every environment. While it works flawlessly within our solar system, perhaps it breaks down in the vast, faint outskirts of galaxies. He introduced a new universal constant, a critical acceleration threshold so small it defies ordinary intuition. When the pull of gravity on a star falls below this limit, Milgram suggested that the force of gravity no longer weakens as quickly. It becomes stronger than expected, allowing stars to orbit faster without the need for unseen dark matter. This simple but profound tweak to gravity produced astonishing results. With just one adjustment, MOND could predict the rotation speeds of galaxies that dark matter theories required massive invisible halos to explain. It could also forecast an exact relationship between a galaxy's visible mass and its rotation velocity, a relation that was later confirmed in hundreds of galaxies with remarkable precision. To many scientists, this seemed like more than coincidence. It was as if the universe itself was hinting that gravity behaves differently at the very edges of galaxies, whispering secrets about a law of nature we still don't fully understand. This single, simple modification was miraculous. With no need for a massive, invisible halo of dark matter, Mond could perfectly explain the flat rotation curves of hundreds of different spiral galaxies. It wasn't just a fit, it was a prediction. A key success of Mond is the baryonic-Tully-Fisher relation, an observed empirical law that connects a galaxy's total mass in baryons, the stars, and gas, directly to its rotation speed. In the dark matter paradigm, this is a mysterious coincidence. Why should the visible matter be so tightly correlated with the rotation speed, which is supposedly dominated by an invisible dark matter halo? Mond explains it automatically. The rotation speed is determined directly by the visible matter, because there is nothing else. For decades, Mond has been far more successful at predicting the dynamics of individual galaxies than the dark matter model, which has to be tuned with a different custom halo for each galaxy it tries to explain. However, Mond's stunning success on galactic scales is matched by its glaring failures on other scales. In its original form, MOND was a modification of Newtonian gravity, not Einstein's general relativity. This meant it was not a relativistic theory, so it couldn't make predictions about the expanding universe, the cosmic microwave background, or the bending of light known as gravitational lensing. Over the years, several relativistic versions of Mond have been proposed, such as Jacob Bekenstein's TVAS theory, but they are often complex, mathematically cumbersome, and themselves finely tuned. More damningly, MOND struggles to explain the dynamics of galaxy clusters. While it reduces the need for dark matter in clusters, it doesn't eliminate it. Mond proponents are forced to concede that there must still be some form of unseen matter in clusters, which they often attribute to massive neutrinos or some other form of hot dark matter. This undermines the original, elegant premise of the theory, that dark matter isn't real. The final, and for many the fatal, blow comes from the Bullet Cluster. This system consists of two galaxy clusters that have passed through each other. We can map the location of the visible matter, the stars, and the hot gas, which glows in X-rays, and we can map the location of the total mass by observing how it bends the light from background galaxies through gravitational lensing. The observation is crystal clear. The hot gas, which makes up most of the baryonic mass, has collided and slowed down in the middle. The stars passed right through, but the gravitational lensing map shows that the bulk of the total mass is located with the stars, having passed right through the collision without interacting. This is exactly what the dark matter model predicts: two halos of collisionless dark matter passing through each other like ghosts, leaving the sticky gas behind. For Mond, this is a nightmare. Since Mond's gravity is tied to the baryonic matter, the strongest gravitational effects should be centered on the hot gas in the middle. But the lensing clearly shows the mass is elsewhere. To this day, the Bullet Cluster remains the most direct and powerful piece of evidence for the existence of dark matter, and the most significant challenge to the MOND paradigm. Yet even as modern cosmology wrestles with dark matter and modified gravity, ancient wisdom reminds us that human knowledge is limited. In Islam, the vastness of the universe is seen as a sign of the Creator's power, a reminder that not everything unseen is unknowable. The Quran describes the heavens and the earth as purposeful creations, balanced and precise, reflecting an order beyond human comprehension. In that sense, whether we call it dark matter, modified gravity, or something yet undiscovered, the mystery itself may be part of the divine design. So, who is right? The reformers, with their clever adjustments and exotic physics, or the revolutionaries, who demand that we tear down the old models and start anew? Which side will ultimately win the war for the soul of cosmology? The truth, the climactic reveal of this entire cosmic detective story, is that we don't know. And in a profound way, that very uncertainty is the answer itself. The single most important revelation from the James Webb Space Telescope is the death of certainty. For decades, the story of the Big Bang was told with growing confidence. It evolved from a daring hypothesis to a widely accepted theory, its predictions confirmed again and again with astonishing precision. We believed we had the cosmic story all mapped out. It felt like a blockbuster movie where everyone already knew the plot. But then came the James Webb Space Telescope, and in its first year, it tore up the script. It cancelled the sequel, ripped apart the first chapter, and threw the pages into the air, reminding us that we might not be nearing the end of the story after all. We might be standing right back at the beginning. And in science, this is not failure. This is not something to fear. This is the very heartbeat of discovery. In his groundbreaking 1962 work, The Structure of Scientific Revolutions, Thomas Kuhn described how science does not simply move forward in a straight, predictable line. It advances in cycles. For long periods, it operates in what he called normal science, where researchers solve puzzles within an accepted framework, a paradigm. This paradigm isn't just a theory, it's an entire worldview, a shared language of assumptions, methods, and trusted models. For cosmology, the Lambda CDM model has been that reigning paradigm for over 3 decades. Scientists have spent years refining its parameters, calculating the exact amount of dark matter, mapping the cosmic web, and detailing how galaxies and stars form within it. But then, anomalies start to appear, facts that don't fit the story. At first, they're brushed aside as errors or exceptions. But when they persist, and when multiple teams confirm them, the old paradigm begins to crack. Science enters a crisis stage. It's chaotic, uncertain, even uncomfortable. Yet it's also a time of intense creativity, the moment when humanity's understanding of reality expands. From that chaos, a new paradigm can emerge, a more powerful framework that explains not only the old facts, but also the new mysteries that the previous one could not. History is filled with such revolutions. For over 1,000 years, humanity believed in the Earth-centered model of the universe proposed by Ptolemy. It worked reasonably well, but to explain strange movements of planets like Mars, astronomers had to keep adding more and more circular epicycles, making the model absurdly complicated. Then came Copernicus, who dared to put the sun at the center. His idea was simpler, but not immediately accepted. It took decades of observation and the genius of Galileo, who saw moons orbiting Jupiter, Kepler, who discovered elliptical orbits, and finally Newton, who revealed the universal law of gravity to turn the tide. A complete paradigm shift from Earth at the center to the sun changed everything. The same thing happened centuries later. At the dawn of the 20th century, Newton's universe was still the unquestioned truth, but small anomalies began to disturb its perfection. Mercury's orbit didn't match Newton's predictions. The Michelson-Morley experiment found no evidence of the ether wind, proving that the speed of light was constant for all observers. These stubborn facts didn't fit the old physics, and from those cracks emerged Einstein's relativity, a radical new view that redefined space, time, and gravity itself. Today, the discoveries from the James Webb Space Telescope may be the first tremors of another such revolution in cosmology. We are living in the crisis phase right now. It's thrilling, unnerving, and profoundly historic. The universe is challenging us once again to think bigger, deeper, and differently. The ultimate lesson of these impossible galaxies is humbling. The universe is not here to fit our expectations. It doesn't owe us simplicity or comfort. It is not our story to write. It is our story to discover. And perhaps, as the Quran reminds us, every sign in the heavens and the earth is there for those who reflect. In Islam, this search for understanding is not a rebellion against faith, but an extension of it. A way to witness the greatness of the Creator through the mysteries of creation. The further we explore, the more we realize how little we truly know and how perfectly balanced this vast cosmos is. So, what happens now? The work begins again, deeper observations, bolder theories, and an ever-growing sense of wonder as we continue our endless journey to understand the story of the universe. Astronomers are now racing to confirm and expand upon these extraordinary findings. The first step for any suspected early galaxy is spectroscopy. An image, even from a telescope as powerful as the James Webb, is just the beginning. It shows brightness and color, but not certainty. By studying how much redder a galaxy appears than expected, astronomers can estimate its distance using a method called photometric redshift. Yet, this technique can be deceiving. A nearby galaxy heavy with cosmic dust can appear deceptively red, mimicking the color of one that lies billions of light years farther away. That's why spectroscopy is the gold standard, the universe's ultimate fingerprint test. When astronomers pass the faint light of a distant galaxy through a prism-like device known as a spectrograph, the light splits into a rainbow of wavelengths. Hidden within that rainbow is a crucial marker, the Lyman break. At a specific ultraviolet wavelength of about 91.2 nanometers, hydrogen gas becomes opaque and blocks light from shorter wavelengths. This creates a sharp cliff in the spectrum. By measuring where that cliff appears, astronomers can calculate precisely how much the light has been stretched by the expansion of the universe, and therefore how far back in time they are looking. Early spectroscopic confirmations from research programs like the JADES or James Webb Advanced Deep Extragalactic Survey have now come in, and the results are stunning. These galaxies are real. They are as ancient and massive as they first appeared, and their very existence challenges everything we thought we knew about how quickly the cosmos could grow. But the mission is only beginning. Astronomers are now pushing even deeper. The Uncover Project, Ultra Deep, NIRSPEC, and NIRCAM observations before the epoch of reionization is using giant clusters of galaxies as natural telescopes. Through the power of gravitational lensing, the immense gravity of these clusters bends and magnifies the light from faint galaxies behind them. This allows the James Webb to peer even further back in time, perhaps to the very first generation of stars. the legendary Population 3 stars. These ancient stars, forged from pure hydrogen and helium, might appear not as hazy galaxies, but as solitary, dazzling points of light shining from the cosmic dawn. Finding even one would be a holy grail of modern cosmology. Meanwhile, back on Earth, theorists are engaged in an intellectual war, one fought not with telescopes, but with the world's most powerful supercomputers. Modern cosmology no longer lives only on chalkboards. It unfolds in vast digital universes. Simulations like Illustris, TNG, EAGLE, and CAMELS create virtual boxes of space billions of light years across, filled with dark matter, gas, stars, and the laws of physics. Scientists press play and watch a universe evolve across 13.8 billion simulated years. Now, these simulations are being rewritten from scratch to face the James Webb crisis head-on. Researchers are adding new ingredients inspired by the reformers, those who believe the standard model just needs tuning rather than replacement. They're testing whether primordial black holes could have served as seeds for massive galaxies, running simulations with and without them to see which matches real data. They're experimenting with different types of early stars, tweaking how massive they were or how violently they exploded. They're testing new ways gas could have streamed into galaxies, faster and more efficiently than ever imagined. And the debate doesn't stop there. Some scientists are questioning the very nature of dark matter itself. What if it isn't cold and slow-moving, as long believed? What if it's warm dark matter, made of lighter, faster-moving particles that smooth out smaller structures but help large galaxies form quickly? Or perhaps it's fuzzy dark matter, made of ultralight quantum particles with wavelengths spanning entire galaxies. In that case, the strange, wave-like nature of matter could rewrite how galaxies form and evolve, removing the dense central cusps that standard cold dark matter predicts. Every assumption is now under fire. Every constant is being retested. Scientists are locked in a frantic digital race to build a simulated universe that mirrors the one James Webb is revealing. An ancient, vast, and humbling cosmos that refuses to fit neatly into human theories. And while this great scientific struggle unfolds, it's worth remembering a deeper truth. Throughout history, every major discovery has reminded us of our smallness before the universe. The Quran beautifully captures this spirit of reflection in verses like, "Indeed, in the creation of the heavens and the earth, and the alternation of the night and the day, are signs for those of understanding." This pursuit of knowledge, of seeking signs in the cosmos, isn't just science. It's a timeless human calling, one that bridges curiosity and faith, intellect and awe. In the end, we find ourselves back where we began, standing beneath the same vast sky, staring into the darkness, asking the same eternal questions. We pointed our most powerful instrument at what we believed was the beginning of time, a technological eye forged from our deepest desire for certainty. We expected affirmation, a clean, ordered picture of the universe's first moments, the prologue to a story we thought we already knew. Instead, the universe looked back, and it surprised us. In a blaze of ancient, impossible light, it didn't confirm our expectations, it shattered them. The cosmos revealed not answers, but a beautiful mystery. The impossible galaxies of the cosmic dawn are not flaws in our data. They are cracks in the mirror of our understanding, an invitation to be humble before the infinite. They dare us to question, to wonder, and to embrace uncertainty not as defeat, but as discovery. Our models are not the universe itself. They are merely maps, and maps are always incomplete. JWST has shown us that our cosmic chart, the one we once believed was nearly finished, contains vast, uncharted regions marked with that ancient warning. Here be dragons. And that is a wonderful thing, because it means that the age of exploration is not over. It has only just begun. This cosmic reckoning is already shaping the next half-century of astronomy. The Nancy Grace Roman Space Telescope, set to launch in the late 2020s, will be the next great explorer, a surveyor rather than a deep stargazer. With a field of view 100 times wider than Hubble's, Roman will scan immense swaths of the sky, finding not dozens, but thousands of ancient galaxies. What JWST began as a mystery, Roman will turn into a map. These numbers, the great cosmic census, will become the crucible in which our theories are tested. Do these galaxies favor primordial black holes, a cyclical universe, or something we haven't yet imagined? Meanwhile, on Earth, the next giants are rising. In Chile's Atacama Desert, the extremely large telescope, ELT, is taking shape. Its 39-meter mirror ready to capture 13 times more light than any telescope before it. In Hawaii, the 30-meter telescope, TMT, is planned to join it. Together, they will dissect the galaxies Webb and Roman discover, one spectrum at a time. They will measure the motions of their stars, the fingerprints of their elements, and the echoes of their ancient births, performing autopsies on light itself. These instruments, working in harmony, will decide the fate of modern cosmology. Perhaps they will find that the Big Bang model survives, refined, expanded, but still standing. Perhaps primordial black holes or new laws of star formation will reconcile the data. Or perhaps they will uncover something even deeper, evidence that the universe has cycled before, or that gravity itself behaves in ways we have yet to comprehend. We do not know what we will find, but that is the point. Science has never been a monument to certainty. It is a journey from illusion to insight, from comfort to curiosity. The universe does not owe us simplicity, it offers us wonder. We stand on the edge of a new cosmic frontier, gazing into an undiscovered country. These galaxies are not the end of our story. They are the beginning of a new one. They remind us to look at the night sky, not with complacency, but with reverence. Because the universe, it seems, is still full of impossible things, waiting for us to find them. Thank you for staying with me till the very end of this cosmic journey. If you're still here, it means you share that same spark of curiosity, that beautiful urge to understand the universe we call home.